A surprising look inside the atmosphere of a distant sub-Neptune. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. This week we explore TOI-270d, an exoplanet observed by JWST that's giving scientists a window into the most common type of exoplanet in our galaxy, sub-Neptunes. I speak with Chris Glein, principal scientist at the Southwest Research Insitute and lead author on a new preprint paper that blends atmospheric chemistry, geophysics, and Earth-based analogs to decode this mysterious world. Surprisingly, figuring out whether or not an exoplanet hides an ocean of water or an ocean of magma can be really complex. But with the right tools, we're getting closer to the answers. Then we'll get a space policy update from Jack Corelli, our Director of Government Relations. He'll unpack the U.S. President's new skinny budget request. It proposes a 24.3% cut to NASA overall, including a staggering 47% reduction in its science program funding. That's the largest request cut in the agency's history. We'll talk about what happens next and how scientists, advocates, and global partners are pushing back. And as always, we'll wrap up with What's Up with Bruce Betts and a brand new random space fact. Before we move on, just a quick reminder to all of those asteroid hunters out there. Proposals are open for the 2025 round of the Planetary Society's Shoemaker Near-Earth Object Grant Program, but the deadline is fast approaching. If you're an amateur or a professional astronomer tracking near-Earth objects, you'll want to check it out. The deadline to apply is next week on May 14th. You can learn more and download the request for proposals at planetary.org/NEO grants. Now, let's take a mental journey across the vast distances between stars to a world unlike our own. The exoplanet we're talking about today is TOI-270d, a sub-Neptune orbiting a red dwarf star about 73 light-years from Earth, in the direction of the constellation Pictor. It's part of a compact system that was discovered by NASA's TESS mission in 2019. TOI-270d is about 4.8 times the mass of Earth. It takes about 11.4 days to complete its orbit and circles a star at a distance of 0.072 astronomical units. That's less than a fifth of Mercury's distance from our sun. This world is giving us a chance to learn more about the most common type of exoplanet found in our galaxy, sub-Neptunes. They're all over the place, but we don't have any in our solar system, meaning there's a lot that we don't know about them. But who doesn't love a good mystery, especially when it could teach us so much about the search for life? Are they scaled-up rocky planets, gassy mini-Neptunes, or somewhere in between? Investigations of other sub-Neptunes have introduced a tantalizing possibility that some of these exoplanets may be Haitian worlds. Haitian being a portmanteau of the words hydrogen and ocean. These worlds could have thick hydrogen-rich atmospheres and global liquid water oceans underneath. That would make them amazing candidates for habitability, even if they're nothing like Earth. As it turns out, TOI-270d is probably not one of those Haitian worlds, but the science done to figure that out gives us a deeper understanding of other sub-Neptunes that could have those conditions. The most famous Haitian candidate so far is called K218b, which you may have heard about because it's been really hot in the news recently. We'll talk more about that later in our conversation. TOI-270d is giving scientists the chance to look deeper into sub-Neptune atmospheres than ever before. Using data from the James Webb Space Telescope, Chris Glein and his team have found a rich mix of carbon dioxide, methane, and water vapor, and also a few surprising absences that could reveal what lies underneath the atmospheric layers. Dr. Chris Glein is a planetary geochemist and principal scientist at the Southwest Research Insitute in San Antonio, Texas. He studies the chemistry and evolution of ocean worlds in our solar system and beyond. His research combines spacecraft data, lab experiments, and chemical modeling to uncover the conditions that shape worlds, and to explore whether or not life can exist elsewhere in the cosmos. Chris is one of the field's leading experts in the geochemistry of icy moons. He was last on Planetary Radio in July 2023, sharing his work on phosphorus, an essential ingredient for life, in the oceans of Enceladus. His team's new preprint paper is called Deciphering Sub-Neptune Atmospheres, New Insight from Geochemical Models of TOI-270d. It was accepted by the Astrophysical Journal on April 13th, 2025. Hey, Chris, welcome back on Planetary Radio.
Hi, Sarah. Great to be back.
So, your newest paper, which is currently in pre-publication, analyzes the atmosphere of an exoplanet called TOI-270d, which is a sub-Neptune. And this world is being called a kind of Rosetta Stone for this class of planet. What makes it such a valuable target?
It's a really interesting target. It is one of these sub-Neptunes, and these are mysterious planets to us. They're smaller or less massive than Neptune, but they're bigger than Earth. And so we don't have any examples of sub-Neptunes in their solar system. But yet we've learned since the Kepler mission over a decade ago that this is the most abundant size class of planets in the galaxy. So there's a lot of questions people have about what these planets might be like, what's lurking deep down in these planets. TOI-270d was particularly interesting because it's relatively close. It's a sub-Neptune that's only about 70-some light years away from Earth. And the James Webb Space Telescope was able to get really incredible data from TOI-270d. And that helped to unveil what at least this particular sub-Neptune looks like it is.
Yeah, the paper makes a strong case that this world is not necessarily a water-covered Haitian world, but there are some alternative possibilities. Why does that matter for our understanding of sub-Neptunes more broadly?
So I mentioned that the sub-Neptunes are mysterious. Some of these sub-Neptunes, the bigger ones, they have densities. So that's how much mass per volume. The densities are in this no person's land where there's a lot of different possibilities. They could be massive rocks covered by some gaseous atmosphere, or an alternative possibility is they could be huge ocean worlds. And they've been nicknamed Haitian worlds, where it would be a large liquid water ocean, and above that would be a hydrogen atmosphere. And these were hypotheses. And when James Webb started collecting data, people were very interested in what these worlds might be like, because you can imagine, on the one hand, if it's a Haitian world, that could be a really interesting place to look for biosignatures or to think about the possibility of life on these types of planets, these most abundant sized planets in the galaxy. Or if they're large super Earths with superheated atmospheres, that's also really cool scientifically, because we've never really dealt with that type of planet before, and we can learn more about how planets work.
Yeah, there's so many repercussions to this in the search for life ultimately, but also just our understanding of this most populous type of world in our galaxy. It's really interesting that we don't have one.
Right. And it's also interesting to me because the stakes are so stark. You have, on the one hand, you almost have like a heaven, right? Where it's this glorious place to be swimming in alive. And another place, it could be a literal hell, where there could actually be molten rock. The entire surface could be covered with a molten rock ocean. We call it a magma ocean. So it's an extreme contrast. And we were really looking forward to getting more data to try to unravel this mystery.
Yeah, I mean, even among terrestrial worlds, we see the difference between something like Earth and Venus, right? So there's got to be a lot of diversity among these sub-Neptunes, but I love the idea that there might be these Haitian worlds out there, but it's going to take a lot of digging to figure out what is what and overall more broad patterns about how these worlds behave. But in the study, you mentioned quenching quite often. Can you explain what that means in the context of planetary atmospheres?
Right. It's a really jargony word, right? So what it basically comes down to is it comes down to chemistry, where if you're deep down in a hot atmosphere, molecules are reacting with each other like crazy, and they reach a state known as chemical equilibrium. And that's a really convenient state, because we can calculate that quite simply just based on the temperature, pressure, and chemical composition. But then as you go up an atmosphere, temperatures slowly decrease. And while the temperatures are decreasing, molecules start moving around slower and slower, and reactions start to slow down. And eventually, the molecules have so little energy available that reactions stop. And at that stopping point, we say the reaction is quenched. And we think that quenching occurs some distance down into an atmosphere where it's still pretty warm. And then as the molecules get lofted upwards, we see the molecules preserved in this quenched state.
So, how do these quenching conditions help us understand kind of not just the structure of the internal atmosphere, but also its mixing?
Yeah, it's a huge tool. It's a window into the deeper atmosphere to understand mixing, because you can imagine if mixing is very fast, there's not a lot of time for molecules to adjust. So they can get quenched at very high temperatures deep down. And so by looking at these molecules in the atmosphere using James Webb and other space telescopes, we can figure out, okay, did it quench, at low temperatures or high temperatures, and then that can help us understand how well mixed the atmosphere is. And ultimately, with that kind of understanding, we can piece together how representative the atmosphere is of the entire planet.
In this case, you were detecting the abundances of methane and carbon dioxide and water vapor and trying to, estimate where these chemicals were quenching in the atmosphere. What did that actually teach you about the internal temperature and pressure conditions?
Right. So I have to explain that I wasn't the one personally doing the detections. It was a great team led by Bjorn Benneke and the rest of his JWST team. They wrote a paper last year where they presented the data, and these data are utterly spectacular. So they deserve all the credit. We use their data, and then we try to take the next step to learn about what's going on deeper in the planet. What we found is that the quench conditions appear to be similar, or in fact, even warmer than the surface of Venus.
Oh,
Yeah. So it gets hot pretty quickly when you go down this atmosphere. And we think that if you extrapolate even further, you could reach a global magma ocean really far down at the planet's surface. You could have this incredibly hot atmosphere, the stifling atmosphere, and that atmosphere is trapping heat, which allows a magma ocean to survive.
man, that just paints a picture. It's just absolutely terrifying, but also really cool.
Yeah, it's utterly bizarre and wonderful. And what's convenient about a magma ocean is people have been puzzled about a particular type of molecule known as ammonia. It's a nitrogen atom bonded to 3 hydrogen atoms. We were expecting to find ammonia in the atmospheres of these sub-Neptunes because we find ammonia in Jupiter's atmosphere and the atmospheres of the ice giants in our solar system. So we're expecting ammonia, and it was argued that if we didn't see ammonia, that might suggest that a planet would be a Haitian world, because you would need a huge liquid water ocean to remove the ammonia so you don't see it. That was the logic. But it turns out that if you have a magma ocean present, magma under certain conditions, like we think exist on this planet, has this phenomenal capacity to absorb ammonia and nitrogen. So it's a great way to make the ammonia soluble, not in liquid water, but in liquid rock.
Does the oxidation state of that magma matter for how much of this it absorbs?
It matters hugely. So what the oxidation state is, it's a tendency of the environment to take up or release oxygen to different molecules in the atmosphere. On the Earth, we're familiar with very oxidized conditions because we have free O2 in the atmosphere. But on these atmospheres of sub-Neptunes with a lot of hydrogen, that's in a chemically reduced state. And people have done experiments to show that if you have this really reduced state of the system, like on these sub-Neptunes, then the liquid magma, we call it a silicate melt, it has this great capacity to absorb nitrogen from the atmosphere. So it's like a huge sink. The entire surface magma ocean is a huge sink of nitrogen atoms.
So the ammonia is missing, but your team kind of took that a step further, showing that total nitrogen might be depleted in this atmosphere. I'm wondering how you determined that, considering that molecular nitrogen is actually really difficult to detect with our current technology.
Yeah, that's true, because N2 is a perfectly symmetrical molecule. You can't see it very easily using a telescope. But what was convenient in this case, I mentioned the quenching earlier, because we were able to use the observations of CO2, methane, and water, we could determine what the temperature pressure conditions are of quenching and then apply that to nitrogen species that we can't see. So we could then predict how much N2 there should be or how much ammonia there should be coexisting at those quench conditions in the atmosphere. And we found that the atmosphere is remarkably depleted of nitrogen atoms. Even N2 that we can't see, we don't expect it to be very abundant because ammonia wasn't seen as well.
So does that mean that, potentially, if we're not seeing ammonia or a lot of nitrogen in these sub-Neptunes, because I'm sure there are going to be some that have it, that might be able to be a differentiator between which ones have this, Haitian world thing going on versus magma ocean underneath.
It could help. This planet actually suffers a double whammy potentially. So it has the magma ocean, we think, on the surface, which can take up the nitrogen. But then we also think that the planet itself might be depleted in nitrogen. We did a really thorough investigation of planetary building blocks. In our solar system, these are known as chondrites. They're the leftover remnants of when the planets formed. And it turns out nitrogen is an element that's particularly prone to being depleted in the rocky building blocks of planets. So that can also provide an added push in explaining the apparent absence of ammonia.
I love that you kind of compared all of this data to real solar system analogs, the CI chondrites, and also Comet 67P, one of my favorite comets. But why is it so powerful to use that instead of just using purely theoretical models?
That was one of our goals of the paper that we wrote, was trying to get this crosstalk going between people who study solar system planetary science and exoplanetary science, because they offer the exoplanetary science finds these utterly bizarre worlds that we're trying to understand. But in the solar system, we have a ground truth. We have a sense of what the planetary building blocks are like. We have a sense of how chemistry works in atmospheres. So we thought it'd be useful to try to apply these tools to an exoplanet. And we are also really interested in trying to approach the problem from many different directions. So one direction I call is the top down. So that's like taking observations and then inferring what's going on inside a planet. But then you can also go from the bottom up, where you say, well, what if the planet formed out of meteorites? Or what if it formed out of comets? Can we find a path to explaining what we see at present?
That's just one example of real life things you compared it to, but you also use these volcanic fumaroles or fumaroles. So how's that pronounced?
Oh, yes, no problem. So they're called fumaroles. So if you've ever been to, like hiking up to the volcanoes in Hawaii, or if you've been to Mount Vesuvius before, you see these cracks in the ground where there's like superheated gases coming out. You don't want to really get close because you might hurt your nose if you sniff in too much of the gas. Those are fumaroles. And what we use the fumaroles for is they provide a real world example of gas chemistry. When you have a hot gas present in a subsurface environment. So we're able to use insights that geologists and geochemists have obtained from studying fumaroles to try to apply it to understanding hot gas chemistry on an exoplanet.
That's so cool. I love how all of these things connect together, that our understanding of our own planet can just so enhance our understanding of other worlds, even if there's something as different as a sub-Neptune.
Yeah, exactly. I'm totally with you. I love to try to connect the puzzle pieces. It's great fun, and I think it can be powerful in opening our minds up to more possibilities.
Right. And one more example of why so many of these sample return missions, either from comets or asteroids, but even from other worlds like Mars, could be so helpful for us.
Oh, yeah, totally. Because we're always surprised. Nature is so complicated and wonderful that we're constantly surprised. And nothing beats having a sample, because you can interrogate it to your heart's content, measure all of the elements way at the bottom of the periodic table, and learn a ton about how processes on planets work.
We talked a little bit about the absence of ammonia, but the JWST spectra also showed that there wasn't any carbon monoxide, or at least very little, in this atmosphere. Why is that surprising?
It's an interesting observation. It's true. So James Webb did not detect carbon monoxide. It's known as CO. And I got to give a little bit of my historical perspective. So I've been on both sides of this argument about Haitian worlds. About a year or two ago, I was originally exploring the Haitian world idea for a different sub-Neptune called K218b. And one of the arguments in favor of the Haitian world hypothesis was that you needed that kind of environment was good at getting rid of CO, whereas a hot atmosphere you would expect to CO.
Mm-hmm.
So that was kind of an inconsistency with a hot atmosphere model. But what was so powerful about TOI-270d is JWST was able to measure the abundance of water vapor on this planet. And that's one of the reasons why it's like a Rosetta Stone, is from measuring the water vapor abundance. Then we were able to understand how the chemistry of CO should behave in this environment if it's a hot atmosphere. And we found that CO can be naturally depleted by chemical reactions involving water in a hot atmosphere. So no Haitian world was needed to explain why you don't see CO.
Interesting.
And TOI-270D, I'm sorry, it's a mouthful. My kids call it the toy planet. Why it's so useful, it's like the Rosetta Stone, is because not only is it close to us so we can get great data, but it's a little bit warmer than K218b. So the water vapor that exists deep down is able to mix well and fully throughout the atmosphere. So we can actually measure the abundance of water vapor. K218b keeps stymieing us because it's cold enough that water can actually freeze out and form cloud droplets or ice particles higher in the atmosphere. So we're stumped as to how much water vapor is actually present in that type of sub-Neptune.
Yeah, the last time we talked about K218b on this show was about a year ago, and we were not only talking about it potentially being a Haitian world and, trying to analyze its atmosphere, but that one was particularly interesting because there was a potential detection of this chemical called dimethyl sulfide, which on Earth is only really created by living creatures, mostly little dudes in the ocean, right? Where are we in trying to figure out how that atmosphere works?
Yes, the plot continues to thicken by the day regarding K218b. I'm sure many listeners might be aware that about 2 weeks ago, maybe it'd be 3 weeks when the show airs, it was announced that astronomers at the University of Cambridge had detected signatures of dimethyl sulfide or dimethyl disulfide in the atmosphere of K218b. So these are special molecules, as you mentioned, Sarah, that contain carbon, hydrogen, and sulfur. They are produced by microbes, phytoplankton in Earth's ocean, so they can be a biosignature, but we need to be really careful. And there's been a lot of discussion in the astronomy and planetary science community over the past few weeks to try to understand what these data are telling us.
Yeah, anytime there's this suggestion of life on another world, people get really, really excited. And I always feel like the science there is so exceptional. And then it enters the news, and all these headlines are so sensationalist that people think, oh my God, we detected life on this world, but we're still trying to figure it out.
Yeah, so I would emphasize patience. I think it's also remarkable, fantastic, really, that we can even start to have these discussions with real data. There are a variety of interpretations and ways to analyze the data, but the fact that we have data that we can start talking about these things as we move closer to detecting life, I think that's wonderful.
Yeah. Just imagine a day where we detect something like, polystyrene in something's atmosphere, and the debate would be insane.
Whoa, yes. Yeah. So one thing I tried to emphasize as that story was developing is we need to be super careful about expecting a smoking gun. I think I was quoting New York Times saying something like, unless ET is waving at us, maybe smiling at us too, we're probably not going to see a smoking gun, because it's a complex universe out there. And we're still learning about many different types of processes on planets. It turns out planets are complicated places. And so it becomes very challenging to try to unambiguously find a biosignature. It's kind of like in a court of law. So if we're looking for life, how scientists approach this is we're like a prosecutor we're collecting all the evidence and we're building up the case. And unless you're really lucky and you get like video footage or something, then it's going to be more challenging. You got to piece together a lot more evidence to make the strong case.
Yeah, we were having this discussion recently when we were talking about the asteroid samples that were brought back from asteroid Bennu by the OSIRIS-REx mission. And these samples literally had all of the nucleobases in it, but that doesn't mean that it has anything akin to RNA or DNA. So, we really have to be careful when we're talking about these things, because the ingredients of life are literally everywhere. But whether or not it's life is going to be something we're going to be hotly debating for a long, long time.
Right, but it's extremely intriguing because the ingredients of life, the so-called building blocks, seem to be formed fairly readily in many different cosmic environments. And then if you look at the history of life on Earth, it looks like life emerged fairly quickly after the Earth started to become a habitable surface environment. So that tends to make many scientists, including myself, very optimistic that we might someday find evidence of life elsewhere.
Oh, I know, right? The search continues, and it's such a worthy one. I cannot wait. But
Yeah,
who knows if
we're
it'll be in
just
our
getting
lifetime.
started. That's
I
true.
know,
We're
right?
just getting started.
Well, going back to TOI 270D, I think something that confuses a lot of people when we're talking about stars or celestial bodies in space, particularly when astrophysicists are talking about these, is that they refer to any element more complex than hydrogen or helium as a metal. What does it mean that this world is metal rich in that context, and why does that matter?
Yeah, I personally don't know exactly the history of how astronomers came to refer to those elements as metals,
Right? It's so weird.
because I'm more of a chemistry background person. So metals for me are kind of like the real metals that you might imagine, like in a nail. But why metals are important in atmospheres is because they tell us something about the nature of the building blocks of these atmospheres. So, for example, comets have a lot of the volatile metals like carbon, oxygen, potentially nitrogen, that can go into planetary atmospheres and lead to a metal enrichment. If you have extensive interaction between, let's say, a surface magma ocean and the atmosphere above it, then the atmosphere can extract some of the volatile elements or metals from that magma ocean and become enriched in metals. So metals are a great way. It's kind of a blunt force tool, but it provides insight into how the planet formed and evolved.
Speaking of which, does this atmospheric composition tell us more about like whether or not this planet formed inside or outside of the snow line? I know you mentioned that a little earlier.
It's a little bit tricky. So James Webb is doing a phenomenal job, but this planet is getting close to pushing the limits of JWST. And so the error bars are fairly large right now. We can do some useful development, but it's hard to definitively say what happened on this exoplanet. Not surprisingly, right? Because it's so far away. But what it seems to suggest is this planet looks like it falls along trend lines between carbon and oxygen abundances for rocks like chondrites, seem to provide a good match to what we see on TOI 270D. And it looks like our giant planets look more like they formed out of comet-like building blocks. So it's tempting. I don't want to say we're there yet because we're really pushing the envelope here, but it's tempting to see this as this planet maybe formed inward of the snow line. So you can imagine it might have formed as like a super Earth that was then able to collect a little bit of hydrogen gas from its formation environment, and that led to the superheated gas atmosphere we find today. Whereas our giant planets appeared to have first formed from lots of little comet snowballs that came together before a lot of gas was captured to form Jupiter, Saturn, Uranus, and Neptune.
We'll be right back with the rest of my interview with Chris Glein after this short break.
Greetings, Bill Nye here. The U.S. Congress approves NASA's annual budget, and with your support, we promote missions to space by keeping every member of Congress and their staff informed about the benefits of a robust space program. We want Congress to know that space exploration ensures our nation's goals in workforce technology, international relations, and space science. Unfortunately, important missions are being delayed, some indefinitely. That's where you come in. Join our mission as a space advocate by making a gift today. Right now, when you donate, your gift will be matched up to $75,000 thanks to a generous Planetary Society member. With your support, we can make sure every representative and senator in D.C. understands why NASA is a critical part of U.S. national policy. With the challenges NASA is facing, we need to make this investment today. So make your gift at planetary.org/takeaction. Thank you.
And it's interesting that there's so many similarities in those trends between this world and our outer planets. But you did mention in the paper that the nitrogen that we're seeing in this world does not follow that same trend.
That's right. Yeah, it looks like nitrogen is depleted. So that might reflect rocky body processes being more important, particularly the magma ocean type chemistry. Whereas I don't think anyone has proposed yet, but maybe it still needs to be studied whether or not the ice giants, for example, might have molten rock or some kind of magma ocean deep down.
Oh, see, one more reason why we need some kind of mission to go back to Neptune and Uranus, because wouldn't that be wild if there was just magma oceans down there underneath all those like raining diamonds and stuff?
You're onto something there because in the paper, we even go on about this. Uranus offers this incredible opportunity because you mentioned earlier that JWST has a really hard time seeing N2, a nitrogen molecule. And that's the key to understanding how ammonia and nitrogen works inside planets like these sub-Neptunes. The beautiful thing about sending a mission to Uranus is we'd be able to send a probe that would parachute down into the atmosphere, and it would have an instrument called a mass spectrometer that could take in the gases and immediately determine how much N2 or molecular nitrogen is present in that environment. So it'd be a great way to complement these developments in exoplanetary science.
So what kind of follow-up observations would we need in order to figure out whether or not this thing actually has a magma ocean or some other nitrogen sequestration situation?
So the initial observations of TOI were recorded by an instrument called NIRSPEC and NIRIS, and this covers a wavelength range of about 1 to 5 micrometers. There's another instrument on James Webb called MIRI. This is the same instrument that was looking for dimethyl sulfide on K218b, that other sub-Neptune. To my knowledge, the MIRI data have not been made available or collected yet from TOI-270d. So that would be a great way to expand our knowledge because MIRI could cover a wavelength range from about 6 to 12 micrometers. So it would effectively double our wavelength coverage of TOI-270d.
So the data hasn't been taken yet, essentially. They just didn't have that instrument turned on when they were doing these other observations?
For the first set of observations, the ones collected by Bjorn Benneke, they just used NIRIS and NIRSPEC because those are actually the easier instruments to use. MIRI is a little more challenging from what I've been told, but I do know the same team, the Cambridge team led by Niku Medusan, they have a program that is going to be looking at TOI-270d and collecting that MIRI data. So we might hear about the MIRI data sometime later this year or next year from TOI-270d.
Nice. And then we can actually try to drill down on this a little bit more and then compare it to other worlds like K218b.
Right. So we'll drill down, but there's all sorts of other sub-Neptunes out there. And I like to say, I don't know if I've said this before on your show, that I view planets are like people. They're so different. They have these different histories. They were born in different environments. So it's not shocking at all to find that these planets are also different and diverse in incredible ways. So we need also, in addition to drilling down on these two remarkable sub-Neptunes, we need to keep looking at other sub-Neptunes to try to figure out, well, what are the similarities and differences among the whole population.
Do you know if there are any other exoplanets that are coming up for JWST observations that would help us with that?
Oh, yes. Yeah, there are many of them in the pipeline. There's many that have been measured. The data are still being studied and papers will come out. There's observations scheduled for this year and next year. I cannot tell you all the names though, because there are all these crazy names starting with TOI or K2 and GJ. But if people are interested, you could definitely search them, and there's going to be a phenomenal pipeline of data coming. So people like myself will have lots of questions to puzzle over in the coming years.
Speaking of which, what do you think are your biggest open questions about sub-Neptunes that hopefully JWST can answer?
I'm interested if there could be Haitian worlds. I think since the announcement a few weeks ago about K218b, the pendulum has swung a little bit towards skepticism. And I think that the arguments in favor of K218b not being a Haitian world are pretty persuasive to me. Mm-hmm. But that does not mean that Haitian worlds do not exist. There's still many other planets further out in different star systems that might be Haitian worlds. because we're currently biased. The easy exoplanets to see are the ones that are close to their star. And when they're closer to their star, they're more susceptible to being superheated. And then that's when you can walk into magma ocean land, right? But if we find some of these sub-Neptunes eventually out in orbits that are comparable to Jupiter or Saturn's orbit, then I think it becomes much more plausible that we could find Haitian worlds.
Man, that would just be so cool to even just be able to identify one and say for sure that's what's going on, because it would just open up the possibilities for places that we could expand our search for life.
Yeah, exactly, because we see these ocean worlds in our solar system like Enceladus and Europa, and they have huge liquid water oceans, we think, by our standards, and we think they could be habitable. But just imagine if you had a planet that's 5 times the size of Earth with an ocean that's hundreds of kilometers deep, and there's hydrogen gas in the atmosphere. There could be geothermal or atmospheric sources of energy. This is a really interesting environment to contemplate whether life might have gained some kind of foothold.
Yeah, on these smaller moons, there's tidal forces and, latent heat from their formation, all kinds of things that heat up these worlds that could allow for that energy to, form life, or these hydrothermal vents that could help us form life around them. But for a world much larger than that, it's not difficult to explain the temperature conditions necessary to make a suitable condition for life.
Right. And even beyond just the life question, understanding chemistry or oceanography. I like to say one of the things I'm trying to do is create like a galactic oceanography or an astro-oceanography. And we're starting to put some pieces together, finding these ocean moons in our solar system. And if there are some exoplanets that might be huge water worlds, then that opens up the real estate even further.
Well, the last time you came on our show, you were speaking about phosphorus in Saturn's moon, Enceladus. And I tell you, people were so excited by that episode, we ended up having to rerun it because it was one of our most popular episodes of the year. and
so that's great.
Seriously, clearly there are a lot of people out there that really want to know more about this. So, hopefully someday there's going to be whole degrees on, exo-oceanography. It's a comparative field. That would be so cool.
Yeah, it would, because I think we'll be shocked when we learn what's possible on these other planets far away. Things we can't even imagine may very well be happening out there. The unknown unknowns. And that's actually what drives a lot of exploration. What drives exploration for many people, including myself, is not to confirm our hypothesis, but we just go out there because we want to learn more about the universe and the solar system and what's actually possible. And I think that's one of the great things that NASA does, is to help us explore.
Yeah, it's that classic question of like, well, what do you think you're going to find? We don't know. That's why we're going.
Yeah, but to me, it's totally okay to say we don't know for these kinds of things, because these are big questions. They're hard questions, and we just need more information. As a scientist, I'm perfectly happy and fine to say, I don't know, but let's go find out.
Well, you have been studying all of these ocean worlds out there. Other than this specific exoplanet, are there any other worlds that you're currently looking into?
There's another really interesting exoplanet. It's called LHS 1140b. That planet appears to possibly be a supersized ocean world. James Webb also observed that planet, and its atmosphere looks unlike K218b or TOI-270D's atmospheres.
Like, how so? How is it different?
It has what we call a flat spectrum. So when you see a lot of I should go back a second. So the way JWST studies molecules in exoplanet atmospheres is a planet transits in front of its star. From our point of view, it's like a mini eclipse, and the starlight will then filter through the planet's atmosphere, and certain molecules in the atmosphere will absorb some of the starlight, and then we can see different wavelengths of light that are blocked through that transiting event. And so then we can identify, okay, there's CO2, methane, and so forth. And if you have a big atmosphere, these types of atmospheres that are prone to making magma ocean surfaces, you get much larger features because the atmospheres are puffy. So you can really see the CO2 and methane. They're very well defined. But for this other planet, LHS 1140b, the spectrum looks flat, but yet the planet is big. It's a super Earth type planet. So we think that it has volatiles on its surface like water, but yet we don't see these really magnified features. So it looks like it might have the potential to be covered by water, and it would have an atmosphere that's more akin to what we find on Earth or Venus, for example, where it could be mainly CO2 or N2 dominated atmosphere.
That's so cool.
Yeah, so we're very interested in what might become of that planet as astronomers continue to collect data. They're very good, by the way. All these astronomers that have done this work are phenomenal scientists, and all this work would not be possible without them, and as well as the James Webb Space Telescope, which keeps on delivering.
Yeah, we knew that this telescope's capabilities were going to just open up the entire field of comparative exoplanetology, but like the things that we have been finding with it, even just in a short amount of time, just really speak to why it's absolutely worth investing in these long-term projects to build telescopes of this size. Because it took several decades and it did go quite a bit over budget. But that being said, the results are so worth it.
Yeah, they are. The scientific payoff is incredible. The payoff in prestige is incredible, and the payoff in inspiring the next generation and training the next generation of scientists, that's also incredible. So we got to keep it all going.
Absolutely. And thank you so much for bringing us this really cool planet. And next time you find some other world out there that's totally blowing your mind, come back and let us know.
Thanks for your interest, Sarah. Great questions.
Thank you. Now we bring our focus a little closer to home. NASA, the largest space agency on Earth. The people behind many of the telescopes and missions we rely on to explore space, is facing the largest proposed budget cut in its history. To help us understand what's happening and what it means for the future of space science and exploration, I'm joined by Jack Corelli, the Planetary Society's Director of Government Relations, for a space policy update. Hey, Jack, welcome back.
Hey, Sarah. Good to be here.
Well, in previous weeks, we've spoken a lot about the passback budget for NASA and what was going on with that, but there are new developments and a new form of budget out, the skinny budget. Can you tell us a little bit about what all of these different steps in the budget process are like and how far are we away from the full budget?
Yeah, so this is, for all intents and purposes, this is the budget request. This is that next evolution of what we saw leaked just a few weeks ago. The skinny budget, as it's called, is officially titled the President's Budget Request. You will notice that this is a very short document, 46 pages. Government does a lot more things than just 46 pages worth. This is just your top line. Here are the agency level funding requests for the across the federal government, for all the agencies, departments, and various entities within the federal government. That top line funding request. And so not everything gets in here. But this is, the difference between this and passback is that this is official. This is the administration saying, here are our top line policy priorities for all of these agencies and departments, and maybe some key highlights. For NASA in particular, I will say it's not only as bad, but actually worse than what we saw in passback and what had been rumored. There's cuts in here to things like the International Space Station that I don't think a lot of folks in the community were expecting. And really, I mean, this is a 24.3% cut to NASA. This is, no stipulation needed, the largest downturn request in NASA's history for its budget. There has been no point in NASA's history, not even the end of Apollo, that has seen NASA's budget shrink by this amount. That's huge.
That's huge.
Right? In this budget, we see a 47% cut to the Science Mission Directorate. The budget specifically calls out the Mars Sample Return Program, a program that we've advocated for, that's been a long-standing goal of the planetary science community, that step before you're able to send humans, since we've been talking about this in the 1970s. So Mars sample return specifically gets called out, saying it's canceled. It's done. There is included in this budget, it claims, a $1 billion budget line for a future crewed Mars program. It makes a very interesting argument that, well, people will bring the samples back from Mars. It has very little details on what that would entail, who would run it. Theoretically, it's a NASA program. It's under the NASA program line. But there's not much clarity about what that path forward is. I, for one, would prefer to have the robots go and come back before I got on a spaceship to Mars. And that has been the expectation of this moon to Mars architecture. That has been the definition of the human exploration program going on 6 years now, 7 years almost. The Trump administration in the first term established Artemis and that roadmap to go back to the moon in the 2020s and then onward to Mars. And Mars sample return played a role as a key science mission, but also as a technology demonstration for that ability to safely and successfully return high-value objects or people from the Martian surface, something that no other nation has done before, but that other nations are committed to doing, whether that's the European Space Agency, who's providing the return ride for the American samples that Perseverance rover is currently collecting, or the China National Space Program, which has identified Mars sample return as the next key step in their astrobiology strategy for the next 20 years. So I think, back to an earlier question you asked, what is the next step in this process? So Skinny Budget has come out confirming all of the leaked information that came out earlier last month. But there's very little in terms of exact policy prescriptions or decisions or funding levels beyond just this really top-line NASA top-line budget, right? And then some indication of, well, here's how much we're going to increase human space exploration and decrease all these other areas. I will say, if you read the budget request, this doesn't even necessarily line up with the way that NASA is formally structured as an organization, like with the mission directorates and offices. And so it's kind of hard to parse like where exactly some of these cuts are going, to what divisions within science. There are things like the Office of STEM Engagement that get zeroed out completely. Oof. So the next step is getting that full congressional justification, the CJ as we call it. That will be the 400, 500, 600 page light reading that will detail each program line that exists within NASA. And every department and agency within the federal government does this. But for NASA, it'll go through line by line and say, here's how much we're going to spend on the Mars exploration program. Here's how much we're going to spend on the Cosmic Origins, which is one of the program lines under astrophysics. And so it's going to go through all those and hopefully lay out a cohesive policy. How the Office of Management and Budget, led by Director Russ Vought, how they're going to translate that into actual policy action, right? This is just real top line. Here are the levels, but there's no cohesion between them. One of the common themes in here is talking about, the United States wants to beat China back to the moon, but then goes on to say that we're going to more or less hand off the moon program to an unnamed commercial entity after Artemis 3. And so there's not a cohesive policy strategy underpinning this document, at least not one that is publicly available. Mm-hmm. What we'll see at the end of May is that congressional justification that hopefully will illuminate what that policy prescription is.
Well, this is all very dire, and we're in a bad situation here, but I'm really heartened to know that so many people in the United States and elsewhere have been speaking out on this issue, whether or not it's through our Action Center or other places. Even the European Space Agency just came out with their statement about this. And we've seen just a huge upswell of people signing on to our open community letter. We talked a little bit about this last week, but what's the update that's happened in the last 7 days?
It's been an amazing, I guess, pedal to the metal, right? I mean, the number of organizations that have signed on, we've nearly doubled the number since we initially put out the letter just in the middle of last week. And it ranges not just scientific or advocacy organizations like the Planetary Society, but also includes actual scientific societies. So like the American Astronomical Society and American Geophysical Union that represents practicing scientists, to the American Institute of Aeronautics and Astronautics, another society, but primarily representing engineers, to groups like the Planetary Science Institute, which is the largest private institution representing planetary scientists in the world. And then you have groups like the Commercial Space Federation and Coalition for Deep Space Exploration, which are trade associations, which represent the interests of the commercial space industry. The science program, 47% cut, that is a lot of science. And that's not something you can just turn off and on. You can't just go on Indeed, a year from now and say, I want people that understand how to land on Mars. Oh, but they all got laid off last year. You can't just turn that expertise back on. This isn't just something that can change over the course of quarters or a year or two. This is culture and organizational memory, things that exist beyond generations. And that is what led NASA to be the spectacular space agency that it is today, operating 140 space science missions in development and operation, and the International Space Station, and the Artemis program, and all these other things. A downturn like this is a serious existential threat to the agency, and in particular, science.
We've got so many updates coming out about this that we can't really cram it all into this show. And we want to make sure that people are up to date on what's happening with the NASA budget, because we need everyone on board to help us with this, to advocate for NASA science. So we've created this beautiful new thing. I'll let you announce it to everyone.
Yeah. So if you go to the Planetary Society's website, planetary.org, on the homepage, you'll see a button for an action hub, a Save NASA Science Action Hub. All of the letters we're working on, the policy updates we're receiving from the field here in DC, opportunities for you to get engaged in this process and to be an informed advocate. We've put it all in one place in this Action Hub. So head over to the Planetary Society's website, and it has all the information you need in there. There are updates from me and Casey as things are developing. Like I said, we've seen this huge influx of support for this open community letter, up to 16 signatories already and growing. Wow. Those updates are all going to be in there, as well as, again, those opportunities for you to get engaged. And for folks who are not in the United States, please also consider going to the Action Hub to stay up to date about what's happening here that might be of interest to you. And we're working on ways to facilitate advocacy globally. As you mentioned earlier, Sarah, the European Space Agency put out a statement. They don't really put out statements about the policies of other governments very often, but this is such a shift in direction for NASA that they've felt the need to do that. And so working with our colleagues in Europe and all over the globe, we want to give folks an opportunity to have their voice heard here in the United States and globally, because this is, as we all know, so readily that the space exploration endeavor that we go on, whether it's with people or robots, is international. Every mission has some component or some instrument that's provided, whether it's NASA providing it for another nation or international organizations like ESA providing instruments for our spacecraft in the United States. The soft power of NASA is huge. Technological ability of NASA is huge. The economic impact and the way that it can act as that seed funder for the industries of tomorrow is huge. The scientific discovery that it enables is huge. We need NASA, and we need you to join our effort.
Thanks, Jack.
All right, thanks, Sarah.
Now let's check in with Dr. Bruce Betts, our chief scientist here at the Planetary Society. He's here for What's Up and a new random space fact. Hey, Bruce, what's up?
Life, Sarah, life.
Life, man. Yeah, we had a whole gamut of conversations in this episode this week. I mean, everything from sub-Neptunes to what's going down in DC with the NASA budget. So honestly, life continues.
It's up and down.
All right.
But we're going to make a difference.
Yeah. Well, I mean, it's been really heartening to see how many people are writing in, how many people are joining on to our letters. And also hearing stories from behind the scenes about how committed a lot of Congress people are to trying to turn around this NASA budget thing. So I'm definitely heartened, and no matter the outcome, we're all in this together, and it's been really wonderful seeing everyone rally.
Rally, really rally, really rally.
Let's go. But so in this conversation with Chris Glein, we talked about sub-Neptunes, we talked about the chemistry of planetary interiors, all this kind of thing. And one of the questions that I brought up, which is something I've wondered as someone who studied astrophysics, despite learning all about star metallicity and that kind of thing in school, I'm still curious why it is that astrophysicists decided that they wanted to call anything heavier than helium a metal. So I'm just going to put this to you. Like, why would they call those things metals, considering that they don't follow the definition of metal in the chemistry sense?
I'm sorry, but I don't know why they picked metal. I mean, obviously, part of the reason was because they got to use the word metallicity, which is just a fun word to say. And metallicity indicates how much it's got stuff that's heavier than helium. And you do form metals in the late states of stars sometimes. And the sun has a metallicity of about 1.4%. So most of the mass is, of course, hydrogen and helium. And when you get low metallicity stars, that's when they haven't absorbed in all the wonderful metals that aren't really metals that others may. It's very confusing.
It is really interesting, though, to think that most of the universe is still, after all this time and all this different nucleosynthesis, it's still mostly just hydrogen and helium.
Yeah. Hey, how about would you mind if I went on to a little something else?
Well, let's do it.
A little bit of
Not bad. You should join a metal band.
For right now, let us focus on the random space fact, which is, you remember Dimorphos and Didymos, the DART mission went and slammed into one of them?
Yeah.
Well, we have official naming conventions for the different bodies out there. And for those, any feature that they found named after a percussion instrument, because DART slammed into one of them like hitting a drum with a stick. And they use percussion instruments from all sorts of different cultures. But that's what they've named features on either body, after percussion instruments.
That's awesome. Although I will say that drumsticks don't do nearly as much damage as DART did to Dimorphos.
Yeah, you're not really a heavy metal fan, are you?
Not really.
All right. But in the meantime, go out there, everybody. Look up at the night sky and think about the wind gently blowing through the hair on your head, the leaves in your yard, and your pet's fur. Thank you and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week to talk about the successful sample collection on the moon with Lunar Planet Vac on the Blue Ghost lunar lander, the first successful commercial moon landing. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who love the idea of Haitian worlds and magma oceans alike. You can join us and help space advocates around the world stand up for science funding at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.